Okay, Pedro, you asked for it. For that radical equation, I thought I would take you through one that actually is not that bad. It's a radical equation that contains two radicals. And the general strategy when you have that situation is to isolate one of the radicals. So for this particular problem, I chose to isolate the radical 2x minus 3, so I took the other two terms to the other side, and then I'm going to square both sides. And I did that over here in scrap paper, but let me show you what I did. When I square this side, I go like this, mentally or on scrap paper, and I square this side. And when I square this binomial, I have to do what I did over here. You have to use the pattern for squaring a binomial. So this is the word so. So the square root of x plus 7 minus 2, the quantity squared, results in this right here, a trinomial. Square the first term, double the product of the two terms, square the second term. So that's where the right side of this came from this work over here. Now, once you've squared both sides, now you're down to one radical. So we want to isolate the term containing the one radical. So I move everything over to the left side, leaving that radical by itself. And I square both sides again, which is what I did. Again, over here using the pattern a minus b, the quantity squared, I get a trinomial. Here I have to square each factor of this one term. So negative 4 squared is 16, and the square root of x plus 7 squared is x plus 7. Now I got a quadratic equation, and I simplify, set it equal to 0, tried factoring, and it does factor into x minus 42 times x minus 2. So my possible choices for the original radical equation are 42 or 2. But I have to check both of them to make sure one or the other works. Well, when I check 42, I actually get 9 minus 7 is 2, but 2 plus 2 is 4, not 0. So 42 gets rejected. But 2 does work. 1 minus 3 is negative 2. Negative 2 plus 2 is 0. So that's the solution to this one. Okay, so that's the general pattern to follow when you solve a radical equation containing two radicals. Now let's look at the problem that you sent me. Whoever made up this problem is fairly sadistic in my opinion. Okay, so I chose to isolate the radical x squared plus 5, so I took the 10 minus 3x to the other side and wrote it this way. Squared both sides using, again, over here, I just get x squared plus 5 because that's what's under the radical. Over here, I have to square this binomial. So it's a minus b, the quantity squared. Square the first term, double the product of the two terms, square the second term. Then I collected similar terms and isolated the square root of 10 minus 3x. Well, here's the mess. I mean, when I square this side, I get this mess right here. I mean, this is purely sadistic. And to do that, I took x squared plus 3x minus 54 times x squared plus 3x minus 54. I had to be very careful that I did my multiplications correctly, that I combined similar terms correctly, etc. Square this side, I get square the negative 14, I get 196 times 10 minus 3x. And distribute, collect similar terms, set it equal to 0, and now the question becomes, how do you solve an equation like this? Well, there is a theorem that It's called the rational root theorem that says if there's a fraction or an integer that makes this equation true, it must be, if leading coefficient is 1, then the root, rational root, must be a divisor of 956, the constant term. So you could try 1 and -1, 2 and -2. These add up to 11, and 9 is 20, so 3 is not a root. 4 you could try. The point is, at some point in time, you're going to learn what's called synthetic division in order to see if you can identify integer or rational roots of this equation. It's called synthetic division. The only reason I tried -2 is because I knew by the graphing solution that -2 was an answer. So if you use synthetic division on this polynomial, and what these numbers are here are the coefficients of the left-hand side, 1, 6, -99, 264, 956. If you use synthetic division and the remainder over here is 0, that means that this number right here is a root of this polynomial equation. So if I put -2 in here, I will get an answer that sets this equal to 0. So how does synthetic division work? Well, I'm not going to go into too much detail, but what you do is you bring down that leading coefficient, then you multiply. -2 times 1 is -2, add 6 plus -2 is 4, multiply, -2 times 4 is -8, add -107, -2 times -107 is 214, add 478, -2 times 478 is -956, add, the remainder is 0. That means -2 is a root, and that implies that x plus 2 is a factor. So I could rewrite this left side as x plus 2 times this mess right here. And where did that mess come from? It came from these coefficients right here. So it's possible that this thing factors. Well, it turns out it doesn't. But if you go to Desmos and actually graph this function, you will find out that it has a root that's approximately -14.043. To get an exact root, solving a cubic equation is a long, ridiculously involved process. And we're not going to get into that. But the fact is, you do have to check -2, I should say, in the original quadratic, and you do get 10 minus plus 6 is 16, so you get the square root of 16. Put -2 in here, 4 plus 5 is 9. Does that equal 7? Yes, 4 plus 3 is 7. Check. So -2 is a root. If you try to check -14.043 or something approximating that, you find out that it doesn't work. So -2 is the only solution. Here's a picture on Desmos of me graphing g, which is this function right here. So it does, g is the factored form. And you see that that has a root at 2, 0. It also has the root at this -14.043, but if I take f of -14.043, it's not even close to giving us a value of 0. So -2 is the only root. And wow, sadistic to put a problem like this in some kind of algebra practice. I mean, bordering on ridiculous. Okay, but I'm going to end the video and hope that at least gave you some clue as to how to do this.